Using cellular automation to simulate gas flow. Simplified model. Let's do a quick recap of cellular automation. Cellular automation starts with an array of cells, and each cell can have one of several states, and the change between states is governed by a set of rules. The most famous example of cellular automation is Conway's life. In this model, a cell can be alive or dead, and the rules tell each cell to look at the number of neighbors around it to determine its next state. If a dead cell has exactly 3 neighbors, it moves from dead to alive. If a live cell has exactly 2 or 3 neighbors, it stays alive. If a live cell has more than 3 or fewer than 2 neighbors, it dies. The concept behind cellular automation is that these simple rules can lead to complex and unpredictable outcomes. Let's look at the rules for our gas flow model. We start with the cell, which we surround by other cells called neighbors. Since we have 8 neighboring cells, we call this an 8-cell neighborhood. If the position of our cell is at the origin 0, 0, then we can define the location of each neighbor based on its offset from the origin. For example, our neighbor to the north is at x0, y-1. We'll define a set D to hold all these vectors, and a set N to hold the index number of the neighbor itself. So our first neighbor is to the north. We move its direction vector into D and replace it with its corresponding index. We continue to do this for the rest of our neighbors. Now we're left with a set of neighbors in N and a set of corresponding vectors in D. This allows us to locate all of the neighbors for any given cell simply by enumerating the neighbors and substituting the vector in D corresponding to that neighbor. For example, our 6th neighbor is equal to our xy location plus element 6 out of D. We substitute D and then add. So neighbor 6 is at x minus 1, y plus 1. Rather than discrete states, which wouldn't be sufficient to represent our gas pressure, we'll assign a gas pressure value to each cell. Let's say that our cell has an initial pressure of 50, and that its neighbors have varying pressures. Some are higher, some are lower. We'll visualize this with color. All the red cells are higher in pressure, all the green cells are lower in pressure. As we look at how to calculate the new value for our cell, we can imagine that gas always flows from a higher pressure to a lower pressure. So that's rule number 1. Pressure flows from higher to lower. Effectively, this means we can ignore neighbors of higher pressure. We'll get back to them later. Rule 2. A cell must contribute a portion of its pressure to all lower pressure neighbors. Later, when we evaluate the higher pressure neighbors, they will contribute some of their pressure. So that brings us to rule 3. A cell can receive contributions from multiple neighbors. In order to support this, we're going to use what's called a posting model. In a posting model, we start with all 0 values, and then we simply add a little bit at a time as we contribute to the new value from each of the cells as we evaluate them. At the end of our evaluation cycle, we've posted all of the little pieces that add up to our new values of N, and we substitute that for our next frame and begin the process all over again. Going back to our cell and its neighbors, before we dive into the calculations, we have to tackle one more technical problem: diagonals versus cardinals. Cardinals have a distance metric of 1 as they are immediately adjacent. What this means is that if two squares of unit 1 directly touch, then their centers are 1 unit apart. However, diagonals are 1 unit apart across the x-axis and 1 unit apart along the y-axis. So we have to use Pythagoras to help us figure out the distance, which is the square root of the x distance squared plus the y distance squared. In this case, 1 squared plus 1 squared is equal to 2, and therefore the diagonal distance of our diagonal neighbors is the square root of 2, or 1.414. If we invert 1.414, we get 0.707, and any number times its inverse is equal to 1. We'll use this later as we calculate whether a cell's pressure is greater than its neighbor, and again when we determine how much of its gas it contributes to its neighbor. It's implied that we'll use p times 1.0 for the cardinals and p times 0.707 for the diagonals. Okay, let's dive into the calculations. First, again, we're using an 8-cell neighborhood where the cardinals have a distance metric of 1 and the diagonals have a distance metric of 1.414. If the distance metric is m, the pressure of the local cell compared to its neighbor is p times 1 over m. So for cardinals, we simply use p because p times 1 equals p. For diagonals, we use p times 0.707. 2. We define the local cell to be A. N is the set of cells where Ni is less than A.
So these are all of our remaining neighbors except the 3 that we know are higher pressure.
Let's go ahead and label them for clarity. In our example, set N now contains cell numbers 1, 2, 3, 4, and 8. 5, 6, and 7 have been removed from view because they're
Greater in pressure.
than our local cell A. So let's go ahead and label these guys. 3. C sub n is equal to the count of elements in n. In our example, there are 5 elements of n, so Cn equals 5. A prime is equal to A plus the sum of n divided by the count of n plus 1. A prime is the new value of A, and this is a fancy way of saying that A prime is the average of the local cell plus all of its neighbors. In our example, A is equal to 50, so we add 50 to the sum of all of its neighbors and divide by 5, which is the number of neighbors we have, plus 1. That gives us an average pressure of 20, which is the new value for A. A prime is the average pressure. Delta A, or the change in value, change in pressure, is simply equal to A minus A prime. 50 minus 20 is 30. T is equal to the sum of A minus each element of n. So again, our neighbors' pressures are 5, 0, 10, 30, and 25. We subtract A from each of these, and then add up their value, which is 180. So T is 180. 7. Now we create a delta n for each neighbor. We do this by taking delta A, which is the total amount of gas pressure that A gives up as it transitions from A to A prime. As it moves from 50 to 20, it gives up 30. And we distribute this by subtracting A from each neighbor's value, then dividing by the total. So this gives us a proportional distribution for each new cell. As we substitute the values of n, subtract, and then divide, we see that we're left with a decimal number that, if added together, adds up to 1. So the sum of all of these little pieces is equal to 1, and then we use that as a percentage of delta A to distribute to that neighbor. The next step is to post all of the little pieces of A into the right boxes
to reflect the new value for A and its contributions to its neighbors.
Let's talk about input and visualization. Again, we start off with our array of cells. We have three types of cells: air, wall, and pressurized gas. As we build our model, we start off with all air cells. Then we'll build a wall or a couple of walls and add some pressurized gas inside the container we created. So a very simple way to build this model is to start with a bitmap. We paint the walls, we paint the gas on a white background, and then the bitmap becomes our input. We do this by overlaying the cell grid and then extrapolating each color into a cell type. So during our visualization, as the model runs, obviously the walls will stay black, but we need some way to represent the air pressure as it changes from pressurized gas into air. So we need a gradient between these two. At the top, we have zero pressure, which will be represented by a completely white cell. And at the bottom, we have our max pressure M, which will be represented by a completely red cell. Something with a gas pressure in the middle will take a color somewhere between 0 and M.
A 32-bit color value consists of 4 bit fields.
8 bits for alpha, 8 bits for red, 8 bits for green, 8 bits for blue. We assume that the color is always opaque, so we set alpha to FF, or 255 in decimal. The remaining colors, or channels, red, green, and blue, can vary between 0 and FF, or 0 and 255 in decimal. So as a function, we can take the inputs for red, green, and blue and manipulate them to create this bit field, which will return a 32-bit color value. We do this by simply using bit shifting and OR to put all the fields in the right place. Now we have a function that takes 3 channel values and returns a 32-bit color. Each channel value ranges from 0 to 255. On the one hand, we have white, which we get when we have 255 in each of the 3 channel values, which is the maximum value you can have in each channel. And on the other hand, we have red, which you get when you have 255 in the red channel and 0 in the green and blue channels. So the next step is to define a function where we always get a value between 0 and 255, but that gradually goes from 255 to 0 as our pressure approaches M. So 0 pressure would result in 255, a pressure close to M would result in 0. So we start off our function by simply subtracting in order to invert the value. If we subtract P from M, we now have a function that returns a value in the range of M to 0. So we're heading in the right direction. Next, we divide by M. That gives us a value in the range of 1 to 0. It gives us a fraction. And if we multiply that fraction by 255, we now have a complete function that ranges from 255 to 0. Going back and plugging that into our RGB function, we can simply take our pressure, run it through function R, and then submit the value of R for the green and blue channels. So our resulting color value would be 255 in the red channel, R in the green channel, R in the blue channel. As pressure approaches M, the value of R drops to 0, making that cell more red. As the pressure approaches 0, R will increase in value all the way up to 255, making the cell more white. We can add one more step to our visualization. Often we get a fractional value, and it's kind of nice to see the actual pressure envelope, the edge of the pressure envelope. So we'll just put an if statement at the beginning of this that says if pressure is greater than 0, but less than 1, then we'll just plug a nice calming yellow in there. Otherwise, we'll execute our function for R. The final step is to talk about thresholds. So what we've seen so far is just a variance in pressure across the map. However, the other element to this is how quickly pressure changes. If we define a threshold and then compare that threshold to our change in pressure, so if a cell's pressure jumps from low to high, we can color it green, or high to low, we can color it blue. That gives us a way to visually see how the gas is flowing. If we ignore our pressure map for a minute, this takes us to our second visualization. We can build a velocity map by simply counting the number of times each cell either flips from low to high or high to low, and then create a gradient scale. And that gives us a map that looks like this. Disclaimer: this is not a perfect simulation. This is not meant to be a perfect simulation. This is a computer science toy and serves as the prototype for more complex simulations yet to come. Simulation 1. AirZooka. An AirZooka is a device that's basically an inverted funnel with a piece of plastic and a rubber band at one end. If you pull back the rubber band, it sucks air into the funnel. As you release the rubber band suddenly, it creates a vortex by quickly flushing the air out of the funnel. Simulation 2, we're going to point two AirZookas at each other, slightly offset. Simulation 3, a silencer with angled baffles. Simulation 4, a silencer with square baffles. Simulation 5, a wing at 0 degrees angle of attack. Simulation 6, a wing at 45 degrees angle of attack. In conclusion, we've demonstrated a proof of concept. We've shown that we can simulate complex systems using cellular automation. Future works. A better approach, rather than looking at gas pressure, is to develop a vector-based model. So that's probably the next step. I think this approach would also be good for modeling systems of greater complexity, such as predicting storm movement. Thank you for watching, and be sure to visit justinpartek.com.